Okay, I think it's recording now. Um, I don't know how to enable the chat. All I can do is this question and answer thing. I don't know why, because I don't know how to work Zoom that well. If the calcium channels in the heart cells are voltage gated, why do they close when the membrane voltage stays constant? So if you're talking about why do they eventually close after some point on the plateau, sometimes there are channels that they can be voltage gated to open them, and then they close after some period of time. So they don't necessarily require voltage gating to go back down. And I think that's the case for the calcium channels. I will explain that. Science work. Okay, there's a lot of questions. I think I'm going to answer most of them as I go through this stuff, but if not, just yell out to me as I'm going through it. So I'm going to share my screen so you guys can see. Yeah, if I don't answer your question and you think it's a related topic, just yell out to me. That would be helpful. Okay, so what are the factors that determine how ions move? Explain with words and with an equation. So the equation will be just the flux of ions, which is going to just be driving force times conductance. So those are the two factors that determine how ions move: the driving force on the ion and the conductance. So conductance is just how many channels are open. So if there's lots of channels, that's going to increase flux. If there are no channels open, that will decrease flux. And importantly, if conductance is literally zero, it doesn't matter what the driving force is, there's still going to be zero flux for that ion. So in general, we'll have to tell you what the conductance is, unless the special case of neuron action potentials where he said he wants you to memorize the conductances. So you will be given an action potential and you'll be expected to know what the relative conductances of ions are across the action potential. So you should know driving force is actually just the membrane potential minus the equilibrium potential for whatever ion you're looking at. And you should know that the membrane potential is just whatever the neuron's actually at, and the equilibrium potential is a value you have to calculate using the Nernst equation. So the Nernst equation is 61.5 divided by Z log concentration out over concentration in. So on the test, you're going to be given the concentration in and out for different ions. You'll plug them in here. And then, like I said, on the test, the equation doesn't have the z variable. And I'm not quite sure why that is. I would just add in the z, because I think you could get questions wrong if you pretend like it doesn't exist. So the z variable is just the charge of the ion. So you would put a +2 there if it was calcium. You would put a -1 there if it was chloride. And you put a +1 there if it's sodium or potassium. So it doesn't matter for sodium and potassium, it's just a 1. But it will matter for other ions, and you should absolutely expect different ions to be on the test. Yeah, question?
Okay, so about that, the charge, I think Dr. Cooper just said he prefers to just say the flux will be inward or outward instead of just putting the charge to the volume. So I guess that's why.
Yes, yeah, I understand what makes sense for him. I just think that it could end up causing people to do things wrong. Because yeah, if you don't put in the z value, you're going to get a different equilibrium potential. And then if you get a different equilibrium potential, you're going to calculate the driving force incorrectly. So I think you can leave out those things if you have a very high level grasp on knowing that you're using numbers that aren't the quite right numbers here. And I'm not sure how that works. I think it's just easier to be like, this is for sure going to get me the right answer, and I don't have to kind of conceptually think about how I'm taking things out or not. Yes, Elliot.
I was wondering if you could give us an example for like a charge of an ion for like either calcium or sodium, something of the sort.
Yeah. We could do, let's do calcium. So let me look up at least what we've done in the past for the numbers. Okay. So calcium is a +2 charge. And let's say inside the cell, it has a concentration of 0.0001. And outside, it has a concentration of 2. And these are in millimolar. This is the numbers for a neuron. They'll be slightly different from what the concentrations typically are in muscles, but just check what the concentrations are on your test and do it. So how would you use the Nernst equation to calculate the equilibrium for calcium here? So what you would do is I would say equilibrium potential for calcium equals 61.5 divided by 2. That's not a z, that's a 2. And then log 2 over 0.0001. And in that case, you would get, I don't know, you guys do it with me, because you should not do this for the first time on the test. But let's see what I get. Okay, I'm pretty sure it's like 132 millivolts. Did you guys get that? Did anyone else get 132? I just want to make sure because I can do math.
I
wrong.
also got that.
Yay. Okay, nice. Yeah, question. Any questions about what I did there?
I was just wondering how much you guys care about sig figs.
I don't care at all about sig figs, and I don't think it would come up on this exam.
Okay, thank you.
And if it does, then I'll make sure in the grading I tell everyone I said this. Yeah, question.
So just to make sure, you divided 61.5 by 2 because it's calcium 2 plus, right?
Yes. So the Z is just
And,
whatever
and
the charge
the,
is.
right, and the number 2 and 0.001 would be given.
Yes. Yeah.
Okay.
Yeah. Another question?
So since we're using calcium for this one, would like the membrane's potential be like doubled because calcium has a charge of 2, or would it stay as like -70?
Yeah. So again, that's kind of his way of conceptually talking about this stuff. I don't like that as much. For me, it's just easier to put 2 in the equation and say 132 is the equilibrium. I'm not sure exactly how to think about it, like feeling something twice. That's just hard for my brain. So if you just put the 2, you don't have to think about it.
So we wouldn't have to like double or divide the membrane potential like 2, just stay as like -70.
Yeah, you can just keep the numbers as they are if you use the Z.
Okay, thank you.
You're welcome. Yeah, next question.
So for the driving force, the reason why you subtract the E-ion thing is because the chemical gradient and the concentration gradient kind of cancel each other out. Is that why you're subtracting?
Yeah, so the driving force is the electrochemical gradient, which is just the fancy word of saying the entire force that the ion feels, considering the chemical and the electrical. So this whole thing is the electrochemical gradient. And it's the difference between the electrical gradient, which is the membrane potential, and the chemical gradient, which is kind of represented by the equilibrium potential. So this is the kind of gradient that dictates ion movement. And then conductance is just saying, well, like there needs to be actual openings for the ion to move. Yeah, next question.
So I was just wondering, since we got one like positive 132 millivolts, does that mean it's like going into or out of the cell, or like does it not tell us that?
That's a great question. So yeah, how can we like take it a step further and now say, can we talk about the actual direction and flux of calcium given this value? So overall calcium flux is going to be the driving force times conductance. So let's just say there is some non-zero amount of conductance for calcium. So we have calcium channels open. And then in order to see what the driving force is, we have to know what the membrane potential is at this time. So you'll have to be given that. So let's say at resting membrane potential what is calcium going to do? Well, at resting membrane potential, the membrane potential is typically around -70. So if we plug that into our equation, we have flux equals -70 minus the equilibrium potential, which is 132, times conductance, which is, we don't know exactly what it is as a number, but we know it's non-zero. So then you would do just adding 132 plus 70, and you would get the overall flux as being -202. How do you interpret that? Sorry, I'm trying to let people in. How do you interpret the sign? So you think about, okay, if this is a calcium ion, how is it going to move around that sign? Calcium has a positive charge. So like charges attract. So if the cell inside has this negative sign, that's actually attracting calcium in. So what you do with the overall sign after you've done this calculation is say, is that going to attract my ion or is it going to repel it? Because calcium is positively charged, that's an attractive force. So that's saying it's an inward force. And the magnitude of the force is 202. So this is a strong inward driving force on calcium. And as long as we have channels open, a bunch of calcium is going to flood in. As calcium floods in, that's going to make the membrane potential become more and more positive. And so you should be thinking in your head that as calcium's flooding in and as the membrane potential goes more and more positive, that's actually going to decrease the driving force. Questions? Yeah. I guess Meghana?
So when you do the flux calculation and it's negative, that means that the inside of the cell is more negative than the outside of the cell, right? And that's why the positive calcium charge is attracted inwards.
Well, because this is actually calculating the difference between the equilibrium and the membrane potential, what you end up getting isn't necessarily what the cell is at. It's just telling you what is the driving force. Is it inward or outward? The sign tells you it's inward, and the number tells you how big the driving force is. So I would say
So
the negative on the 70 tells you that, yes, the cell is more negatively charged inside than outside. But the driving force is a little bit more complicated as to whether it's reflecting what's going on in the cell.
Yeah, so if it's negative, does that mean that it will always be a inward driving force?
As
Or is
long
that dependent
as
on the charge?
as long as the ion is positive. If this were a chloride ion and you calculated the driving force and it was negative, that would actually be saying chloride will want to move out and away from that like charge.
Okay.
So I think that's what, like, it can be complicated to think about, and what Jake doesn't like is having to interpret the sign in that way. I admit is a little difficult to think about. So he tries to avoid it.
Thank you.
You're welcome. Another question?
I'd like to share like a method that I do that I think is a little bit easier to think about. Because I saw this in one of the unit packets from last year. instead of calculating like the flux with the negatives, you could consider just the magnitude of the membrane potential and the Nernst equation. So basically you create like this diagram and you have like directional arrows that's pointing like wherever the chemical gradient is and the electrical gradient is. And if it's pointing like inwards, that's inwards, right? If it's outwards, that's outwards. So you do like, for example, in this example, I did the same thing. The electrical gradient for calcium is pointing inwards, and the chemical gradient for calcium is also pointing inwards. So you would do like the electrical gradient of calcium, which is the membrane potential, 70 inwards plus the Nernst equation 132 inwards, and you add them and you get the same value, 202. And so I think you could think of like the out minus in or out plus out or in plus in as a way to not have to consider the positive or negative, and instead keep in mind the direction.
Yeah.
If that makes sense.
Yes. Yeah. And that's kind of what we tried to do on like with the board work. When we had the potassium board work example. And I did like upload a document going through exactly that method of doing it that some people prefer. So I drew, yeah, like little cells and did a inward and outward arrow for EG and CG. And that's a whole nother way of doing it. And there's a whole document where I walk through how to do that, which can be helpful to some people. I was just showing how to do it as the equation way. But yes, there are many different ways of doing this, which sometimes makes it better and sometimes makes it harder. You just have to pick a way that makes sense to you. But if you get the right answer, then it doesn't matter. I'm going to show one more way too. But yeah, questions.
I was wondering where you would find that document you're talking about.
I sent it as an announcement and it was like board work explanation. And it like walks.
Okay, I'll look through my emails. Thank you.
You're welcome. Question?
So the MB of the calcium, right? -70, that's just something we would have to remember.
The -70, it would have to be given to you.
Okay.
The only thing you are responsible for is calculating the equilibrium potential using Nernst, and then knowing that the driving force is going to be the difference between the membrane potential and the equilibrium potential. That's something you have to know. It's not given to you, this equation. Yeah, next question.
I have a question. So if we were to use the equation to calculate the chloride, for chloride, do we put -1 for the Z value or do we just put 1?
Yeah, you put -1. Let's just do it for chloride too, because I think it's a good idea and something you might have to do on the test. So let's go over it. So let's say an example where I tell you the membrane potential is at +10 millivolts. And you open a bunch of chloride channels and you want to know how they're going to move. So we're trying to find what is the flux for chloride. And I told you a bunch of channels that opened. So now you just need to calculate what is the driving force. Oops. Conductance. So I already know the membrane potential is 10. So now I just have to calculate the equilibrium potential using the Nernst equation. So it would be 61.5 divided by -1 log of the concentration out which if I look it up, it is 110 typically, and 5 inside. All right, you guys calculate this with me because I'm going to do it wrong. I always do math wrong. Did you guys get negative 83? 82.5.
Yes.
Yes.
Hey, okay, cool. Yay. That would be the equilibrium potential for chloride. Now I want to see how it moves, so I'm just going to do plus 10 minus 83. And that would be, just plus 93. So you do, whoop. Okay, so that means, oops, when the membrane potential is at positive 10, the driving force on chloride is 93 in magnitude, and then it's a positive charge, so that's going to attract chloride in. So chloride's going to want to move towards the opposite charge. So overall driving force is chloride ions moving in. The magnitude is 93. Question?
I got 73.
Yeah. Am I doing something wrong? No, it's so because it's minus negative 83. Those two negatives will mean adding. If that makes sense. Does that make sense? You want to be careful
Yeah.
there with the signs because yeah, you can end up getting the wrong magnitude. And that's another reason why I like to just keep the signs there, because if you don't, it can actually lead you to get like 73 or a wrong number. Yes, Sarah.
Hi, yeah. So I was wondering then if it would be like fair game on the exam for him to ask us to calculate the overall flux while giving us like the membrane potential and the inside and outside concentration, and the conductance is just on us for the ions. Is that something that might happen?
He wouldn't ask you to calculate like flux as a number unless he gave you conductance as a number. He might ask
Okay.
what is fair game is him asking you to calculate driving force, in which case you need to know is this.
Got it. Okay, thank you.
You're welcome. Next question.
So the overall flux, right? It includes driving force times conductance, but the number that you got 93, it didn't involve like multiplying it by conductance. Is that what we're supposed to do, or did we assume that we already multiplied?
Yeah, I just ignored conductance. I just said it's some non-zero number.
Okay, but we usually would like multiply it by conductance and the number that we get, like, and then we would interpret, right?
Yeah, I don't think that he would ask that just because we haven't talked about it like that. It's more like calculate the driving force. And then as long as there is some conductance, the driving force is going to reflect what the flux is. Jay,
But then what?
Oh, yes.
Sorry, I was saying, then what's the point of like multiplying it by conductance?
It's acknowledging that conductance has to be some non-zero value in order for flux to happen. And the more and more channels that you have open, the more and more flux you'll get. So it's just as important to determining the overall flux as driving force. It's just we in this class haven't been considering conductance in terms of like a number.
I see. So even in the exam, we want her to like multiply it by a number, like conductance number.
No.
Okay.
Other questions?
Excuse me?
Yes.
Hello. Yeah, I had a question on the previous problem that you were doing with the 132, where you did -70 minus 132. So is the 132 flowing in or out? It's flowing out, right?
The 132 is the equilibrium potential. So positive, when the membrane potential is at positive 132, that's the equilibrium for calcium. That's what it means.
So how do we know whether to subtract or add?
So the equation
to
is
the
the equation for driving force is just the membrane potential minus the equilibrium potential. So
okay. Wait, so this isn't like the problems where we had the Na and K plus flowing in and out, and we had to calculate it like that, like the driving force. This
Yeah.
is driving force, right?
yes, yeah, this is calculating driving force.
Okay, so how do we know if we're like subtracting it or adding it, depending on if it's like out or inside the cell?
So you just use this equation to calculate the driving force, and you're going to plug in whatever number comes out from the Nernst equation there. You're going to plug in whatever the membrane potential is there. And then after you do that, so you're just plugging in the exact numbers that you get. Okay.
Okay.
And then whatever comes out of there, let's say you get a positive number, then you look at your ion and say, is my ion a positive? Then that's a repulsion force. So that's an out force. If you get a negative number and your ion is positive, that's an attractive force. So that's a driving force into the cell.
Oh, okay. So if it was like Cl minus, you'd multiply it by -1. Is that what you're saying? Or...
If it was Cl minus, I would do all of the same things. I would just interpret this last number for my driving force differently. Now, a positive driving force would tell me that that's an inward force on my negative ion. If I got a negative driving force, that's actually telling my negative ion to leave, to go out.
Oh, okay. So you don't multiply it by conductance or anything.
To get the overall flux, it's this driving force times conductance, because both of those two factors influence how the ion's going to move. But I don't see a question coming up where he would just give you numbers and ask you to plug in.
With conductance, or
it's more, I could see him.
I don't remember doing an example like that.
I could see him.
Unless there's like it's 2 plus. Oh, sorry.
I was just gonna say I could see him doing something like, how is it possible for an ion to have a really big driving force but 0 flux? And that would require you knowing that, well, driving force isn't the only factor influencing flux. There's also a conductance. So you could have a 0 flux and a high driving force if your conductance is 0. So kind of conceptually understanding the role of conductance rather than just plugging in numbers is what you should expect.
Okay. And in the case of, okay, and then you said if it's a positive, it's going in to to the membrane? And then if it's negative, it's going out.
Well, it depends on the ion. So if you calculate the
Depends
driving
on the ion.
if you calculate the driving force and you have a positive ion, a cation, then that ion is, you're going to interpret a positive driving force as out and a negative driving force as in. Now, if you have a negative ion, if you calculate the driving force and it's positive, positive, that's an inward force. And if you calculate the driving force and it's negative, that's out.
Okay, that makes sense. So in this case, because it's Ca2 plus, it's positive ion, we have positive, so it's going out.
So
Is that correct?
in this case, when I did Vm minus the equilibrium potential, I got negative 2O2. So that negative sign, what is it? Is it in or out for calcium?
Okay, so it's going in.
Yes, exactly.
It's going in.
Yes.
Okay, okay, thank you.
Welcome. And then over here, when we did chloride, we got the driving forces being positive. Now that's an in for chloride.
Mhm.
All right, Katie, do you have a question?
Yeah, hi. So I was wondering because I was under the impression that when more, say, like potassium ions were inside the cell, it would get closer to potassium's equilibrium potential. But then like the action potentials, when there's repolarization, the K plus is leaving and it's still getting closer to K plus's equilibrium potential. And I was a little confused about that.
So tell me what your question is.
I think my question is why, so if K plus's equilibrium potential was like negative 90, which I think was the standard example that we used, why when all of the potassium leaves, is the cell getting closer to negative 90?
Why when the potassium what?
Why when all the potassium leaves, does the cell get closer to potassium's equilibrium potential?
Because potassium itself is a positive ion, right?
Mm-hmm.
So when a positive ion leaves, that's going to make the cell more negative.
I think I was just confused because I thought that it was like more ions and like all the more potassium ions in the cell, the closer it gets to potassium's equilibrium potential, just like how when sodium fluxes in, it gets closer to sodium's equilibrium potential.
Yeah, I would say that the key is that potassium ions are going to move to get the membrane potential near negative 91. But in order to do that, it could move in or out depending on what the membrane potential actually is.
Okay, yeah, that makes sense.
It's not always in one direction. It's not always coming in.
Yeah. Okay, thank you. That makes sense.
You're welcome. Elliot, do you have a question?
Yeah, I do, just one. So equilibrium voltage and equilibrium potential, they're the exact same thing, right? It's just interchangeable.
Yeah.
Okay, good. Because Dr. Cooper was talking about that and I was very confused. So I'm glad that that's cleared up. Thank you.
You're welcome. Yeah. There's a lot of words we use for the same thing. Sometimes we forget to clarify. Okay, I just kind of wanted to go over one other way you could think about how ions move besides using the equation. So I'm going to do these same examples, but using just a graph. And this is kind of the way I think can make more sense to people. So I'm going to use just a graph of membrane potential. And let's do the same example we did before. So let's say calcium and the membrane potential is -70. So we're going to say right here, -70, that's where the membrane potential is. And then on your graph, you want to put where's the equilibrium potential for your ion, which you use the Nernst, and you would calculate as being positive 132. The driving force is just the difference between what the membrane potential actually is and where the the calcium ion wants to be. And the calcium ion wants to be at its equilibrium. So equilibrium potential is the potential that that ion is going to have no net movement, meaning it's going to be moving in and out at the same rate. So calcium ions, their whole goal in life is to try to get the membrane potential to that value. And they're going to move in whatever way gets the membrane potential to that value. And how badly they want to get it to move is the driving force. So you can see the magnitude of the driving force is just this difference, the difference between the membrane potential and the equilibrium potential. So the farther away the actual value is from the equilibrium, the more badly calcium wants to move because it wants to get the membrane potential back to where its equilibrium is. So that kind of how badly the ion wants to move, that is the driving force. And it represents in the equation just via minus E ion. And then you can think about, again, pretend calcium is a sentient being. And if we have our membrane potential down here, calcium is like, how can I move? What direction can I move to get the membrane potential where I want it? Well, calcium in this case wants the membrane potential to be really way more positive than it is. And calcium is a positive ion. So calcium ions will accomplish what they want if they move in. So how badly do they want to move in? 202 millivolts. In what direction do they want to move? Whichever direction is going to get them to where they want to be. So that's another way that you can think about what the direction is going to be and also what the magnitude is by drawing it out and then thinking about which direction should my ion move in order for it to accomplish getting the membrane potential where it wants to be. So again, if we had a different membrane potential, let's say it was at 134 millivolts, that's where we actually were. Now you can see the magnitude of the driving force is a lot smaller. Calcium is basically at where it wants to be, right? And if we did our equation, it would be 134 minus 132. It's pretty small driving force, just 2 millivolts. And you can see using an equation, I can see, okay, I got a positive number. My ion is positive. So that's actually a force out, a little tiny driving force out. You can also get that direction by pretending calcium is a sentient ion and thinking about what is it thinking at this point, right? So at 134, calcium's unhappy. It wants to be at 132. Which direction can it move across the membrane to make the membrane potential more negative, to get it down to 132? It can move out, right? If calcium, a positive ion, moves out, it will accomplish bringing the membrane potential down. So at any membrane potential below 132, calcium is going to want to move in to get it to 132, to make it more positive. At any membrane potential above 132, calcium is going to want to move out to drive the membrane potential down towards negative 32. I mean, towards positive 132. So that's just another way of thinking about it that I really like. I like to draw it out. Because it can also help you if you're not sure you're putting in the right numbers. If it makes sense on your like number scale, how big the driving force should be. But yeah. Okay, we can just continue on unless y'all have more questions on that. So ions equilibrium potential, the literal definition is the equilibrium potential is the membrane potential at which there is no net movement. Oops, movement. Of that particular ion, whichever one you're considering. So if we go back here, if the membrane potential is at 132 millivolts, calcium is super happy. It's not going to want to move too much out because that would make the membrane potential too negative, and it's not going to want to move too much in because that would make it more positive. It's really happy where it's at, so it's going to try to do just as much movement in as out. And that's also reflected in the equation, right? So if the membrane potential is at 132 minus 132, the driving force is 0. So no net movement. So yeah, I would think of the equilibrium potential as the membrane potential that causes no net movement of the ion. And it's also kind of that point that those ions are trying to drive the membrane potential. They're always going to move in the direction that gets the membrane potential more near its equilibrium potential. Right. Oop. I thought I put more the other pages in here. I don't know why my other pages are. Okay, hold on. Let me check what the other questions are because for some reason it didn't come up on here. That's weird. I did it last time. I don't know what I'm doing differently. Oh, okay. This is kind of annoying. Oh well. I can click through. Maybe, there we go. Okay, so it says, can you explain how the membrane potential influences ion movement? And that's just reflected in the driving force. Yeah, before I continue, question? No, no question. Or is there?
I have a quick question.
Yeah.
Is there, did you send this document out or is it on Canvas or anything?
Yes, I sent it out as an announcement.
Okay, thanks.
You're welcome.
I have another question. I don't
Yeah.
know if it's just an issue on my end, but for some reason I can't see like the announcement section on Canvas. I don't know if anybody else has the same problem.
I think that's just the setting that someone put. If you access it through the app, it works a lot better. But I can't access it on like the web browser either.
Oh, okay, thank you.
Okay. So I put number 3 just to make sure everyone knows that it's kind of a reciprocal thing where like we did in number 1, number 2, you saw how the membrane potential influenced how ions move by the driving force, right? So whatever the membrane potential minus the equilibrium potential is, that tells you how an ion is going to move. Or if you like the number line, the equilibrium is here and Vm is here. Then this difference is your driving force, which is the same thing as this. So wherever the membrane potential is, the farther it is from an ion's equilibrium, the more movement that ion is going to show, because you're making the driving force really big when you make that difference really big. And then on the flip side, ion movement also influences the membrane potential, right? So when a bunch of potassium fluxes out of a cell, that's a positive charge leaving, and that's going to make the membrane potential more negative, right? Which is what potassium wants. Potassium's equilibrium is typically around -91. And typically we don't have membrane potentials below -91. So most of the time, potassium is trying to move the membrane potential more negative. So as ions move, depending on what their charge is and what the direction of their movement is, they're going to make the membrane potential go up and down. Which means that for a given membrane potential, when you calculate the driving force there, after you have ion movement, you should realize in your head that driving force on that ion is changing as the membrane potential is moving, right? So if we think about like, actually, I think I gave an example here. So at a typical neuron's threshold, maybe around -30, a bunch of voltage gated sodium channels open and sodium ions move into the cell, right? So if we graph the typical neuron action potential at around -30, a bunch of voltage gated potassium channels open, and sodium moves into the cell. That's going to cause membrane potential to increase a bunch to around maybe, like, let's say +40. As this change in membrane potential is happening, this is also simultaneously influencing sodium ion movement because it's changing the driving force, right? So if sodium wants to be at typically around 62, so the equilibrium for sodium is around 62, then as this membrane potential is moving up, we're actually getting closer and closer to where sodium wants to be. So down here, the driving force was pretty big. And as I go up and up and up to the peak, that driving force gets lower. So this initial driving force influenced sodium to move in. And if you calculate the driving force at each of these points, it's still inwards. But the actual amount of flux is going down because the driving force is going down as we get closer to the equilibrium potential. So at threshold, we could calculate the flux of sodium as being negative 30 minus 62. And then let's say we're calculating conductance in number of channels. And let's say that there's like, I don't know, 1,000 channels open at threshold. Now let's consider what's happening maybe right before the peak. So maybe at like positive 30. So then we could calculate the flux as being plus 30 minus 62. And let's say at that point, we're starting to get some inactivation of channels. And maybe it's like 900 channels are open. So you can see the total flux as we move to the top is a lot lower. Number one, because we're lowering the driving force. Right here, it's I guess that would be 92. And over here, it's 28. Is that math? No, is that wrong? I can't do math. 62 minus 30. It's 32. Whoops. 32. So the driving force has gone way down, and maybe the conductance a little bit as well. And then at the peak, the conductance is going to move to be 0. And it doesn't matter what the driving force is, the movement of sodium is going to be nothing. But hopefully you get that as the membrane potential is moving, maybe because of sodium ion movement, it's simultaneously influencing how much flux of sodium is happening because driving force is going to be changing.
Would you explain again, like what's the answer for part B is like in words?
For part B of 3? Yeah, so as an ion moves, it's going to change membrane potential. So you could say like a positive ion going in equals a more positive membrane potential. A positive ion moving out, like potassium, is a more negative membrane potential. Ooh, I don't know why there's such a delay here. Let's read negative. And then for a negative ion, it's just the opposite. So a negative ion like chloride moving in is going to make the membrane potential more negative. And a negative ion moving out is going to make the membrane potential more positive. And then those changes will change the driving force on that same ion. Okay, number 4 says, can you explain how ion movement influences membrane potential when you have multiple ions moving? For example, if I have 2 ions and I tell you their concentrations in and out, and I tell you their relative conductances, can you tell me what the membrane potential should be? So yeah, let's do an example of that. So let's say we have sodium and potassium, and both of them have 100 channels open. Equal number of channels. What is the membrane potential going to be? So what you would have to do is start with calculating what their equilibrium potential is. So given their concentrations in and out, you would use the Nernst equation to calculate. So we can just do that, because why not? So let's say for sodium, let's get some numbers. It is 150 out and 15 in. And for potassium, it is 5 out and 150 in. So Nernst equation, you would say equilibrium for sodium is 61.5 over +1 log out over in. Potassium 61.5 divided by +1 log out over in. And then, because I've done this so many times, I know that you get 61.5 for sodium, and you get -91 for potassium. So that's the membrane potential where they'll have no net movement, and it's also where they're trying to get to. So if I'm graphing membrane potential, I'm going to draw a little line at the bottom, say that's where potassium wants to be. I'm going to draw a line at the top. And I'm going to say that's where sodium wants to be. So if they have equal numbers of channels open, that means their conductance is the same. Then they're both going to be moving with equal numbers of channels to try to get the membrane potential at these two values. And as a result, where the membrane potential is actually going to be is exactly in between those values. So that would be should be around negative 14.75, because that's just the number right in between those two values. Now let's say you opened 50 more channels for sodium, then you would expect the membrane potential to be more near sodium. If you opened 1,000 more channels for sodium, you would expect the membrane potential to be much closer to sodium's and further from potassium. Yeah, question?
Hey, so I was wondering if the membrane potential is pre-established at 70, for example, then when you're calculating the equilibrium potential, then the 65 would be greater, right? It would be around 130. If like the membrane potential is already at 70, then the equilibrium potential for sodium would be at 130, right? Because both of them, it wants to go in like chemically and electrically, so it would bump up more. And so when you're doing the calculations for this value where they're equivalent, you'd have to like change it.
The equilibrium potentials do not change. The only thing that changes equilibrium potential is the concentrations in and out. So if we're at negative 70, the thing that's changing for sodium is the driving force.
So then it would still be 65. It wouldn't be 130 then?
No.
That makes sense.
So the magnitude of the driving force is going to be the difference between negative 70 and 61.5. That's how bad sodium wants to move in to get the membrane potential at 61.5. And so what this question is getting at is there's a tug of war happening between whatever ions are around, and each ion only cares about getting the membrane potential to its equilibrium. And so if you have equal channels for each, the membrane potential is going to fall somewhere right in between. And the more channels you open for each ion, the more votes they have on what the membrane potential is going to be. And the more the membrane potential is going to move towards their equilibrium. Yeah, question?
I was wondering if on the exam, like if we had to answer a question about this, if we would be given relative like numbers for the relative conductances of how many channels are open, or just knowing like more of Na plus versus potassium, or like how to calculate it numerically, I guess is what I'm struggling with.
Yeah, so the only thing that you would need to calculate numerically is the driving force. I don't see you being asked to calculate the overall flux, like as a number. The thing that I would prepare yourself for is to be given like the action potential. It would be fair game for me to ask you, what does flux of potassium look like at here, 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 here? And also, what does sodium flux look like at all of those points? So in that case, I wouldn't ask for a number, but I would want you to say high, low, and then talk about the relative driving force and the relative conductance at each of those points. So we can do that if you guys are interested. Would that be helpful? Put thumbs up or not.
Could we maybe go over it? Sorry, could we maybe go over it like after we've moved on to like heart muscles and like skeletal, or like the heart and skeletal muscles, and then come back to it? Because we might like kind of go over this when we go
Yeah.
over the other stuff.
Yeah, that is true. Let's do that. Okay, I think I can just. Wait. Okay, there we go. I don't know why there's such a delay whenever I'm on Zoom. Very annoying.
I have a quick question. So for the question that we were doing, right, we found the membrane potential is negative 14.75.
Yeah.
So the flux would be 61.5 minus 14.5.
If the
Like the
membrane
difference.
potential was negative 14. Wait, say that again. Sorry.
Right. So the membrane potential that we calculated was negative 14, right? And the equilibrium potential for sodium was 61.5. So the flux for sodium would be the difference between like 61.5 minus 14.5, or like between negative 14.5 and 61.5.
That would give you the driving force.
Right. Okay, I see.
Yeah. Just because flux also, it matters whether there's channels open.
Right. Okay. Thank you.
Oh, okay. I mean the literal next question is going over exactly what I was gonna do. So yeah, we should talk about it. We can talk about it now, actually. So you should be able to say how conductance and driving force and flux changes for the entire action potential. So I'll just do it over here, I guess. And I think another question is how those things change during rest. So we can just do that right now too. So you want to talk about how it's flux, conductance, and driving force changing throughout these different points during the action potential. And first, let's just consider at resting potential, which is right here, and also over here, which is typically around negative 70. So what does flux, conductance, and driving force look like for potassium? So potassium conductance at rest is high. And that's because of potassium leak channels. There is a ton of leak channels that are just little channels that stay open at all times, including at rest. So there's always a high conductance for potassium at rest. Yeah, question?
Can you hear me?
Yes.
Okay, good. So if it was like asking like, oh, what's the potassium conductance at when it's at resting, it'd be asking you to compare to the sodium conductance, not necessarily the conductance of potassium throughout the entire chart. Because like compared to right there, the potassium conductance would be pretty low versus when it's repolarizing, right?
Yeah. Yeah. So I think, yeah, it would be incorrect to just write in high. You would have to say relatively high because there is a large amount of potassium leak channels compared to sodium leak channels. But yes, I agree with you that if you're comparing to, say, the conductance for potassium over here, it's actually pretty low.
Okay, thank you.
You're welcome. So yeah, and I would say at rest, the sodium conductance is pretty low. There's just less sodium leak channels. So this is just something that like he wants you to memorize, but you can also see it just by looking at the value of rest, right? The fact that the value of rest is so close to the equilibrium potential for potassium, it tells you that in this tug of war, potassium is really winning, right? So it must have a really high conductance. Because at -70, the driving force on potassium is actually pretty low, right? If you were to calculate the driving force, it would be the difference between the membrane potential and the equilibrium. So potassium's driving force is pretty small at rest. The driving force on sodium, on the other hand, is really high. So you would expect that the flux of sodium would be winning at that point if driving force was the only thing that determined flux. But because conductance also matters, the potassium flux is a lot higher at rest than the sodium flux. So generally what you should think at rest is lots of potassium leak channels, relatively low driving force on potassium, but overall a pretty high flux of potassium. Hence, that's why the membrane potential is near the equilibrium potential. And then for sodium, you think pretty low conductance, really high driving force, but overall not a really high flux, because otherwise if flux was high, membrane potential would be a lot closer to the equilibrium potential. Okay, the next point we could consider is like after we reached the threshold. So at this point, you should think all of a sudden now we have this huge increase in sodium conductance. So threshold is a voltage that is going to activate all the voltage gated channels. And in this case, there are two. There are voltage gated sodium and voltage gated potassium channels. Voltage gated sodium channels are going to open right away as soon as we hit that threshold value, that voltage. Voltage gated potassium channels, although they become activated at this point, they're a little bit slower to open, and they're not going to open till about half a millisecond later, kind of at the peak. So at this point, we have a huge increase in the conductance for sodium, no change quite yet in the conductance for potassium. And because there's this huge increase in sodium's conductance, now sodium starts to win the tug of war and moves the membrane potential up closer to its equilibrium. As we're moving up, you should also be thinking about the driving force. And like we said before, as we're moving up, the driving force on sodium is going down, and the driving force on potassium is actually going up, right? So way up here, we now have a larger driving force on potassium. Yes, question?
Is conductance like, is that the same throughout?
No,
Like,
conductance
is it just a
changes.
that's changing?
So the driving force is changing, which is what I'm drawing in colors, but conductance is also changing. And the way conductance changes during the action potential is something he just wants you to memorize. He wants you to know that at rest, there's just leak channels, mostly potassium leak. He wants you to know that there's two voltage gated channels that open at threshold. So they're activated at this threshold value. Sorry, not open. They become activated at this threshold value. At this point, voltage-gated sodium channels open, and at this peak point, voltage-gated potassium channels open. So everything I'm saying with the channels opening and closing, you just have to straight up memorize. There's no way for you to know or figure it out with math. You just have to know it, like by memorization. Okay, next question.
Hi, hello. I was wondering why potassium driving force increases when Na is coming in.
Because driving force is the difference between the membrane potential and the equilibrium potential. And as Na is coming in, as sodium's coming in, the membrane potential is getting farther and farther from the equilibrium potential for potassium. So that's what I'm drawing in blue, is the difference between potassium's equilibrium and where the actual membrane potential is. As it's moving up, you're making that difference bigger and bigger. And that difference that I'm drawing here is the driving force. That is just this value. Does that make sense?
Okay, but they're kind of, yeah, I get what you're showing. But there's no potassium coming in. It's just staying the same, isn't it?
Yes.
The
Well,
levels.
what's staying the same at that point for
There's no
potassium
flux.
is the conductance. But I would say the overall flux is changing. So if we think about what's happening at that point, if we were thinking about potassium flux, it's driving force times conductance. So conductance hasn't changed. It's still just the leak channels because we've activated the voltage gated ones, but they haven't opened yet. So conductance is the same, but driving force is actually going up as we move the membrane potential up. So as we move up this way, potassium is actually moving more. So there's actually
Is it
more
moving
flux.
into?
No, it's moving out because
Is it moving in? It's moving out.
yes.
Okay.
Because
Okay.
all of these
Thank you.
values, it's saying, no, go back down. I want to be at negative 91. This is the wrong direction. And the farther you get, the more I'm going to move. It's just that even though potassium flux is increasing, it's nowhere near overcoming the sodium flux. We get like thousands of sodium channels opening, and it's just this huge flux of sodium. And even though potassium is technically going up too, it does not override the sodium push up. Okay, so the next point you should know is the peak. And the peak point, what's important for conductance is sodium voltage gated sodium channels inactivate. So if you were to draw a little channel, it literally has this little like ball and chain thing, and the ball part goes and sits inside the channel tube so that nothing can pass through. So it's not technically closed, but it's inactivated. It can't pass ions. So our conductance for sodium just went nearly to zero because we have all of these channels closed and we have very little sodium leak. So again, if we're thinking about driving force and conductance, at the peak, conductance for sodium is super low. That has gone way down. And then you want to think about what is driving force for sodium at the peak. And it's also extremely low. So overall flux of sodium very low because it's just going to be from those sodium leak channels, which there's barely any. And then also our driving force value is going to be super small. So sodium flux, very small. Then what's going on with potassium? So again, what dictates ion movement? Driving force and conductance. At the point of the peak, we now get a huge increase in conductance for potassium. And if you look at the driving force is also super huge. So potassium flux at the peak is going to be super high because the driving force, that difference, is very big. And then we got all of these voltage gated potassium channels finally opening. So again, that's something you just have to memorize. You have to memorize sodium channels inactivate at the peak and voltage gated potassium channels open. And then from there, you should be able to reason through what is the driving force, what is the conductance, and therefore what's the overall flux going to be for those ions. At the peak for potassium, because there's such a high driving force and such a high conductance from those voltage gated channels, there's a huge flux for potassium, which explains why the membrane potential moves down to where potassium wants to peak. You can see that potassium is winning the tug of war here. Yeah, question?
Yeah, so like it looks like sodium's conductance never increase. It's just its driving for increases and decreases. That's what's driving the flux.
No, the conductance for potassium does change at the peak.
No, not for potassium, for sodium.
The conductance for sodium changes at threshold, it shoots up, and then at the peak, it shoots down because all of the voltage gated sodium channels inactivate.
Okay, so at resting it's low, but at threshold it shoots up.
Yes.
Okay.
And then it goes to zero around the peak. Okay, then we can consider this point down here where the membrane potential actually goes below rest and it's super close to the equilibrium potential for potassium. And what's going on there is, well, what's the conductances happening here? So all we have is a little tiny bit of sodium leak. So there's barely any. Then we have potassium leak. And we have the voltage gated potassium still open. So because there's such a high conductance for potassium, potassium really wins this fight and gets the membrane potential basically at its equilibrium. As we're moving down, as the membrane potential is going down, you should also know that the driving force on potassium is getting lower and lower and lower. So if we were to calculate the actual flux of potassium at this point, it would probably be pretty small because the driving force value is just not that big. Because the difference in the membrane potential and the equilibrium potential is so small, flux overall is going to be pretty small. Once we see the membrane potential go back up to this value, that's when these voltage gated potassium channels are closing. And then that's going to cause the membrane potential to go back to wherever those two leak channels are kind of causing the membrane potential to end up. Yeah, question?
Yeah, at the trough, the point where you're talking, is it the NA leaky channels or is it the sodium potassium pump that pushes it back to -70? Because I remember that being that.
It's a
I'm not
combination
sure.
of it's a combination of both. So the reason why it goes back up to that value, I would say is really because those voltage gated potassium channels are closing. And when the cell is just at rest, it just has those leak channels, and that causes the membrane potential to end up at that value. Now, you could say from another perspective that the pump is also the reason, because the pump is working in the background, kind of setting what the relative concentrations are.
So so just I'm sure at the prof it's just because of the leaky channels, and when it like starts to stabilize, is that the point where the pump kicks in, or like at what point will the pump start working is my question in this
The pump
class.
is, so the role of the pump is to say that I want the concentration of sodium out to be 150 out and 15 millimolar in. And I want the concentration for potassium to be 150 in and 5 out. So the pump makes those concentrations in and out happen. And what that does is it dictates what the equilibrium potentials are, right? Because the way you got 61.5 as being equilibrium for sodium and -91 for potassium was by plugging in those concentrations. So the pump is always working in the background to make sure those concentrations stay what they are, so that the equilibrium potentials stay what they are, and the ions are going to move in these ways because of it.
So it uses ATP when it's active and when so neuron uses ATP when it's active and inactive, right?
Yes,
Because
the
the pump
sodium
is working in the
pump is
background.
always there. Yeah, it's always working at all times. All right. Okay, questions on the action potential? Yeah.
So I'm just a little confused on what exactly causes the like drastic fall after the peak then? Is that caused by the like NA voltage channels closing?
Yeah, so it's a combination of sodium channels closing and a bunch of potassium channels opening up. So it's like you're getting less pull up to 61 because the sodium channels are closed, and you're getting way more pull down towards 91 because a bunch of potassium channels open. So it's both.
So the potassium channels opening are then leaving the cell? Is that why the membrane voltage goes down? In
Yes.
response to that?
Yeah.
Okay.
The channel's open and potassium is like, I want to be down at -91. How can I make that happen? I can leave the cell because I'm positive. Okay, something that might be useful for you guys to look up just to help you visualize this is action. Can y'all see my Google? Can someone thumbs up? It's showing up. Yay, okay. So if you look up the conduct, you can actually graph the conductance during the action potential, which can be kind of helpful to see. See, here's a good one. Okay, so this kind of shows it. So G stands for conductance. But you can see as the membrane potential rises, the conductance for sodium increases, right? And it peaks kind of near the peak, and then it's going to shoot down because that's when the channels are inactivating. But you can see based on this graph, they're not it's not completely zero at the peak. It just starts to decrease. And then you can see the conductance for potassium does not really increase as the membrane potentials increases, but it kind of peaks at the same time as the action potential peak, and then it goes down with some delay, which is why you get that undershoot. So I don't know, that might help, maybe, maybe not. You can also, actually, I might do that. You can also look up the current during the action potential, which is sometimes shown. See if it shows it. Actually, you know, now that I think about it, it might just confuse y'all more. So I'm not. If you want to look up sodium and potassium current during the action potential, and that's going to show you the overall flux of the ions during the action potential. If you're confused by this, I don't know. It could be helpful, could be not. Okay, what would happen to the action potential if you change the normal sodium and potassium conductances? And then I just listed the ones he specifically talked about in his review. So he said sodium channels inactivate earlier. So in that case, what I would expect is if this increase is being caused by the sodium channels, they inactivate earlier. I would just expect that compared to normal, the peak is going to be, it's going to happen faster, right? If sodium channels don't inactivate, I would expect, so it should rise the same. But if they don't inactivate, now I would expect something like this. So what this would mean is that at the peak, instead of getting a huge decreased pull in this direction because the channels inactivate, you're still going to have some amount of pull in that direction from the sodium ions. But at the same time, it should still go down a little bit just because you are still going to be activating potassium channels at that point, which is going to try to pull it down to -91. So I don't think the repolarization phase will go down quite as quickly because you still have such a pull in the other direction. But it still should go down a little bit. And the reason for that is if you have like 1,000 voltage gated sodium channels open and 1,000 potassium voltage gated potassium channels open, potassium's going to win at this point, even if they have equal amounts of channels open. Why? Because it's driving force times conductance. And if they have the same conductance, they both have the same amount of voltage gated channels open, the only thing that's going to dictate where the membrane potential sits is now the relative driving force on each. And at this peak, the driving force on potassium is a lot bigger, right? Because potassium wants to be way down here, whereas sodium wants to just be like right here. So potassium is going to have a larger flux at this point because it has a bigger driving force. So I would say it's going to bring the membrane potential down, not as rapidly, and then the membrane potential is going to just stop and sit at some value in between the equilibrium potentials for sodium and potassium. Okay, and then potassium channels open at a higher voltage. That's kind of a weird one to consider, but I think that was on his review. So if potassium channels don't open until a higher voltage, that's saying they don't actually get activated at the normal threshold. Maybe they get activated at a threshold over here. Well, if this is their activation point, they're still going to open with that delay. So I would say that that would cause the action potential to continue to move up a little bit higher and then come back down at a slightly later point than the normal peak. Just because if potassium channels start to get activated here, it's going to take some time for them to actually open, which means sodium is free to keep bringing the membrane potential up until it inactivates. And then some of that inactivation is going to cause the membrane potential to go back down, but less rapidly. So actually, never mind. I take that back. Forget what I just said. I think, oops. If we have the potassium channels get activated at a higher voltage, let's say they normally open at this point, but instead they're going to open at this point. Because the sodium channels are still going to inactivate at that point, I actually don't think it's going to keep increasing past this normal point. I think because those channels will close, it'll still peak here, and then it's just not going to come down as fast until those potassium channels end up opening. And then it will go down. So I think what you'll see is initially a kind of less quick hyperpolarization until you get those channels finally opening. So overall, I think it would look like something like that. Someone have a question? Okay, so next one. Okay. So that's it for those. We can move on. Okay, why do neuron action potentials move in one direction down an axon? The reason for that is the voltage gated sodium channel inactivation. If you have like an axon and you just had an action potential right here, then the sodium voltage gated sodium channels in this area are inactivated. So current is only going to be able to move this way, and it cannot move backwards the other way because those channels are offline. So the ones next to it will reach threshold, but it can never go backwards. So hopefully that makes sense. It's just the inactivation. Explain everything from number 5 about arresting potential. I think we did that. High conductance for potassium leak, lower for sodium leak. High driving force on sodium, lower driving force on potassium. But overall, that the potassium flux is greater hence why the membrane potential is nearby 91. Okay, can you explain the difference between ion channel proteins and ion pumps? What are the role of each in ion movement? So ion channel proteins are the ones that open and allow ions to move and change the membrane potential. So they're the ones that we talk about during the action potential, right? So you should know, like, voltage gated sodium channels are the reason why the membrane potential moves up. Voltage gated potassium channels are the reason why we get the repolarization. And then there's like, oops. Having trouble with my pen. I don't know what those squares are. This happened last time too. And there's also the leak, potassium and sodium channels. So those are all going to cause ion movement and changes to membrane potential. Ion pumps are just proteins that are working in the background to make sure the concentrations are what they're supposed to be. So the pumps do influence ion movement because, remember, these concentrations give you equilibrium potential, and that is like everything to the ion, right? The ion's going to move at whatever that equilibrium potential value is. So the pumps kind of say what the equilibrium potential is, and then the channels are the ones that open and close and change conductance to allow the ions to move back and forth. Another important point that confuses students is that when channels open, the amount of ions that move to change the membrane potential is not large enough to change the concentrations. So the pumps can change concentrations, but ion movement through channels is too small to change the overall concentrations. Yeah, question?
So is there, so this, so if there was a question where it talks about that the ion pumps are no longer working, what would that look? Would that just move the equilibrium potential up or down a little bit, or how would that make a difference in the graph?
So if they were not working properly, I would say that would mess with the concentrations of potassium in and out. So instead of having this pump, making sure you have a high amount of potassium in and a low amount of potassium out, and a high amount of sodium out and a low amount of sodium in. If the pump isn't working, then you might get the case of those ions coming to equilibrium, and you actually have equal amounts of sodium in and out and equal amounts of potassium in and out. And if that's the case, you've messed with the equilibrium potential and therefore the driving force on the ions, to where if you open channels, they're now not going to move in the directions that we want them to move, right? It's the fact that they have these concentrations that we get potassium rushing in during the action potential, and we get potassium rushing out. And if you mess with those concentrations, they're not going to move in that way. And it's just going to ruin the entire action potential graph, because you don't have these concentrations where you want them to be. Yeah, question?
Yeah, you said the voltage gated potassium channels are what causes the repolarization. What did you say the voltage gated sodium channels do?
So they're responsible for that depolarization.
Okay. Thank you.
Yeah. The reason it goes up is the voltage gated sodium. The reason it goes down is the voltage gated potassium and also the inactivation of sodium. Cool. Okay. Ah. Okay, explain spatial and temporal summation of signals using a graph and a picture. Okay, so we can do an example with neurons talking to muscles. So we have like motor neurons that send synaptic input to some kind of muscle fiber. So how would you draw and graph temporal summation? So temporal summation would be if the signals coming from the motor neuron were in such high frequency that the response in the muscle cell kind of built on each other because there wasn't enough time to clear out the response, the initial response before the next one came in. So you can imagine this motor neuron firing action potentials very quickly like this. And if we somehow were able to record the calcium response in the motor, in the muscle fiber, it would look something like this. For however many action potentials there were. So the first action potential caused an increase in calcium, and before calcium was completely cleared out, the next action potential came in and caused another increase in calcium, and it increased and increased with each signal coming in. So temporal summation is when signals are coming in so quickly that the response is kind of adding on top of the previous one. So that's temporal summation. Once you reach a peak, so you keep sending in signals so fast that eventually you reach some kind of peak in the response, that is what we refer to as tetany. And so how you're getting this increase in calcium in the muscle cell is calcium is coming out of the sarcoplasmic reticulum. And if we were to kind of zoom in on the sarcoplasmic reticulum, we would see there are these channels for calcium. So maybe the first signal activated these channels, and the second one activated these, and then subsequent ones activated these other ones. By the time you're at the peak, you have maximally activated as many channels as are available, and you're getting as much calcium as is possible for that SR to release. Okay, then what about spatial summation? How would you draw a picture of spatial summation? So spatial summation would be now if you had more than one motor neuron. Oops. I think this one's contacting more than just one muscle fiber. Here's another. Oops. Motor neuron. So whereas temporal summation is saying like within one cell and one pathway, the signal's coming in so fast that it builds on itself. Temporal summation is saying you're getting multiple signals from multiple cells that all results in an increase in the overall response. So adding this cell plus this cell plus this cell all firing at once is now causing a larger overall response in the muscle because more and more and more muscle fibers are being recruited. Whereas temporal summation, it might be the same muscle fiber and you're not adding any muscle fibers, you're just increasing the response of that one. So temporal is due to the timing of the input, and spatial is due to how many inputs are converging to create a response. Yeah, question?
Is temporal and like spatial summation different for a neuron versus a muscle?
Sort of. It's a little bit different, but kind of the same idea. So for neurons, again, how I would draw temporal would just be if you had two neurons and one was giving synaptic input, this one was firing action potential super fast, and then you measured the voltage response in the postsynaptic cell, you would see a voltage response that kind of built on itself. And then I would draw spatial summation of neurons, kind of like, okay, you have this postsynaptic cell that's now maybe receiving synaptic input from multiple different cells. And if they all each fire an action potential, it could create one big response in the neuron that's different than responses within one building on each other, if that makes sense.
Yeah, that makes sense. Also, can you give like a real life example of like one example for spatial and one for temporal?
Yeah. So I think it would be helpful to maybe go over like what we did during lab, because lab was kind of an example of spatial and temporal summation. I'm just gonna move over here. Okay. So what did you guys do in the lab? You did 3 different experiments. So experiment 1, you basically changed the voltage by going up by 5s. And you measured the displacement of your frog leg, and you probably got something like this. So you can see that the displacement reached its max value at a voltage of, let's say it's 10 millivolts. So you said that's the voltage needed to get the maximum twitch response in your frog leg. And then in experiment 2, you kind of mimicked temporal summation. So you set the voltage at 10. So each one of your voltage pulses was 10 millivolts, but you changed the frequency that you were delivering it. And I'm drawing this so terribly. So all of these should be the same height. So here, there was no frequency. You just did single pulses. Here you turned up and down the frequency, but you kept the voltage the same. And what you should have got was some data that looked like this. So what this is showing you is temporal summation, right? So your motor neurons, you have some set of motor neurons that are they're activated at 10 millivolts. So all of these pass threshold when you give it a 10 millivolt pulse. And each of those are contacting different muscle fibers. Now what you're doing is changing the frequency at which those motor neurons are firing. So you're making them fire faster and faster and faster. And each of those are going to cause a calcium response in muscle fibers. So that first action potential caused an increase in calcium in all of these cells. And before the calcium could be cleared out of the cytoplasm, you delivered another action potential. So it built up. And then you delivered another one. So it built up. And you delivered another one. And at some point, even as you increase the frequency, it just maxed out because there's only so much calcium and only so much contract response that can happen. And that's when you reach that kind of peak tetany point. And then again, you decreased the frequency of the action potentials from the motor neuron, and that caused these small little changes in calcium in whichever muscle fibers they contacted. So it's actually kind of how quickly those action potentials were coming in that caused there not to be enough time for calcium to be cleared out of the muscle fibers so that the responses kind of built on each other.
So the experiment 2 was the spatial summation.
So this was temporal summation. If that makes sense.
Right, yeah.
Okay, cool. So on board work, we asked you to like do a mass balance representation of what was going on here. And I think the best way to do that is to say you have some subset of muscle fibers, which you draw for mass balance as little containers. And you have that same subset at each point on your graph. So I know I drew 4, 5, 6. But what's happening if we zoom in on any one of those cups is that we're having more and more and more calcium come in from the SR, and the same rate of calcium being pumped back into the SR by the calcium pump. And as a result, you're getting calcium increasing all throughout the increase and also at the tetany peak. Now, if we look at what we did in experiment 3, what you did was now you increased and decreased the voltage. So you didn't hold it at 10 millivolts, and then you measured the displacement response, which should look kind of like a smooth increase and decrease. And this represented spatial summation, because if you were to kind of zoom in on motor neurons in your spinal cord, you would see that they're all different sizes. And the larger cell body motor neurons require more voltage to reach threshold. So now what you're doing is you're not taking some subset and just increasing and decreasing how much you're stimulating them. As you change the voltage, you're increasing the total number of motor neurons that are firing. So maybe before, you were in experiment 2, you were only activating this subset, but you were changing how much you were activating them, how frequently they are firing action potentials. And now what you're doing is you're increasing the total number of motor neurons that are coming online. And as a result, what you're doing, if all of these are connected to muscle fibers, you're going from making a few muscle fibers contract to more and more and more as you increase the total number of motor neurons firing. And so that would represent spatial summation. And how you would draw it with mass balance is now you change the number of cups, right? So here you activated maybe a few cups or a few muscle fibers. And then at the peak voltage, you have activated so many motor neurons and so many muscle fibers that you're getting this huge change in force because you've just activated way more muscle fibers. And then over here, you have a decrease.
Quick question.
Yes.
So for this one, with the spatial, are you still reaching tetany or no?
It depends on what you set your frequency to. I'm pretty sure, I'm not quite sure on this, but I think they say to set it to a high frequency so that all of them are in tetany.
Okay, thank you.
Oh, I don't know where my paper went. Okay, the next question is, how do inhibitory versus excitatory synapses work? And what would you have to change to make an excitatory synapse inhibitory? So excitatory versus inhibitory is just referring to what is the downstream effect on the postsynaptic neuron. So we have, I don't know, a presynapse the postsynapse. If the response in the postsynaptic cell is to increase the membrane potential, then that's excitatory. And if it's to decrease the membrane potential, then that's inhibitory. And how you change between those two is just what receptors are on the postsynaptic side. So, for example, there are receptors that bind to the neurotransmitter GABA. Oops. That are chloride channels. So if a presynapse releases the neurotransmitter GABA, then that's going to activate GABA chloride channels. That's going to cause chloride to flood into the cell and decrease the membrane potential. And so that would be inhibitory. If you change the neurotransmitter and the receptor, then you can change whether the synapse is inhibitory or excitatory. So there are other channels that are for the neurotransmitter glutamate that let in sodium when they bind to glutamate. So it's really the neurotransmitter and the subsequent receptors on the postsynaptic neuron that determine whether a synapse is excitatory or inhibitory. Okay, the next question is, what is the basic signaling pathway for how muscle contraction happens? So the basic signaling pathway is you get a signal in the brain, so like motor cortex sends a signal, so makes a synaptic input to motor neurons in the spinal cord. And then those motor neurons contact muscle fibers. So you get an input from the brain that causes motor neurons to fire, and different motor neurons are connected to different numbers of muscle fibers. So like this one here is only talking to one muscle fiber. So that's a small motor unit. This one here is contacting two, so it's a slightly larger motor unit. And then when the motor neuron fires an action potential, so you get a neuron action potential, that's going to cause an action potential in the muscle fiber. So we can say skeletal AP action potential. So after the muscle fiber fires its own action potential, then if we zoom in on a muscle fiber, we have the actual muscle firing an action potential. That's going to activate a voltage sensor that is mechanically attached to a receptor on the sarcoplasmic reticulum. So that's an RYR receptor. And when this voltage sensor changes conformation in response to the action potential, it's actually going to pull on the RYR receptor, and that's going to cause the RYR receptor to let calcium through. And so a bunch of calcium floods into the cytoplasm. And that's how we're going to get a contraction response, because this calcium is then going to bind to specific binding sites on actin that will expose a binding site for myosin, and that will allow actin and myosin to interact and kind of move past each other by using that power stroke. And that moving past each other is that contraction that, when added up over lots of different muscle fibers, causes the contraction of the muscle. So you don't need to know necessarily the details of like how the steps of the power stroke, but you should know that you need an action potential from the neuron to trigger an action potential in the skeletal muscle. Why does this happen to me? Hold on. Okay, you need to know first neuron action potential, then skeletal action potential, then huge flood of calcium into the cytoplasm via the ROAR channel. And then you need to know that in order to stop the contraction response from happening, you have to get the calcium out. So just as important as the ROAR is a calcium pump that pumps calcium from the cytoplasm back into the SR, ending that contraction response. So that's kind of the basic signaling pathway that you should know. Questions on that?
Yeah, how does the calcium pump know to like push the calcium back into the SR?
It's just constantly doing it
Hmm.
at all times. So,
I have a question.
yeah,
Oh, so that's the same calcium that's used for the contraction, right? That gets pumped back in the
yes,
SR.
yeah.
And then what leaves? Is it just Na leaves, or what leaves the sarcoplasm?
So the sarcoplasm is just a big store of calcium. And when the action potentials come in, calcium will leave the SR and enter the cytoplasm. And after the signals stop coming, then calcium is going to move back into the SR via the calcium pumps. But it's important to realize that the pumps don't change. They're always in the background pumping calcium back in. It's just that during the contraction, more calcium is flooding out via the ROAR. And then when the contraction isn't happening, ROAR isn't active, so the pumps start to win. Yeah, question?
Okay. Oh, sorry, could I ask one more thing? So do we need to worry about how like calcium leaves through the sarcoplasm through another pump, the NCX pump, or we don't really need to worry about that? We're just focusing on the inside, right?
Yeah, the only thing you need to focus on is like, here's my muscle cell. You should know ROAR is how calcium comes out when the muscle fiber is activated, and the pump on the SR is how calcium gets back in. So when the muscle cell is being signaled, this is causing contraction. Then this is going to turn off, right, when it's not being signaled. So calcium ends up net going back into the SR via the pump. Yeah, question?
So in class, we talked about like calcium trickling in and then that triggers the calcium to leave the sarcoplasmic reticulum. Is that only for cardiac muscles and the voltage sensor is different, or are the calcium trickling in from like outside of the cell that triggers a sarcoplasmic reticulum the same as the voltage sensor?
Yeah, so in skeletal muscle, it's a voltage sensor. In cardiac muscle, it's a calcium channel. And so so in skeletal muscle, it's the voltage sensor mechanically opening RYR. In cardiac muscle, it's calcium channels that let in calcium, and the RYR is actually calcium gated. So RYR opens in response to that initial calcium coming in from the calcium channel. But the details of that are not important for you to know. It's just kind of big picture knowing calcium flooding into the cytoplasm causes contraction. When that's not happening, calcium gets out via the pump. Yeah, another question?
Yeah, sorry. You might have gone over this. I was gone for a little bit to take a quiz, but so is the action potential graph for a cardiac muscle pretty similar to what a neuron action potential looks like?
The action potential for a skeletal muscle is exactly like a neuron. For a cardiac muscle, that's the one with the plateau.
Oh, yes, I might have misspoken. Is the reason that the plateau happening because the calcium is being let in? Like there's calcium channels in the cell membrane that get triggered and then calcium gets let in?
Yes, yeah.
So, sorry, this is kind of a long question. So, is the reason that the calcium in a skeletal muscle not contributing to membrane potential as much because it's being used up in the oh, okay. Yeah, got it. Thank you.
You're welcome. Yes, good question. A lot of people have that question. Okay, yeah, so 13 is just kind of getting at the same thing. So passive and active transport of calcium in muscle contraction. So again, it's just this diagram. So the RYR receptor is just a calcium channel. So it opens and it passively lets calcium out, high to low. Active transport is the pump. The pump is using energy to pump calcium against its concentration gradient. It's going low to high into the SR. Okay, 14, I think we already went over. 15, if skeletal muscles only operate at tetany, which of the graphs from last week's lab would never be produced in a live animal? So that would have been experiment 2 that we went over. So what that's telling you is that if we like consider what we were doing, so we were stimulating some neuron to fire action potentials at different frequencies, right? And then we are measuring the response in the muscle fiber. Not directly, we're measuring displacement, but basically as a readout. And the fact that we're saying that this never happens in real life, that tells you that in real life, motor neurons only fire at this high frequency. They never fire little, like one action potentials at a time. The fact that we're saying they only operate at tetany means they're firing whenever they give a signal, it's at such a high frequency that it immediately maximally stimulates the muscle fibers it's talking to. So there will never be a case when this muscle fiber is not kind of maximally letting out as much calcium as possible, because the only signals it gets is at a frequency to where that's going to happen. It will never get such a low frequency signal from a neuron that would cause it to have this kind of weird slow build on itself. Every signal is high frequency, max force on that single muscle fiber. So it's important that you understand that for the test. It's important that you can conceptually understand what it means that muscle cells only operate at tetany. So if you don't understand that point, that will cause you problems on the test. Okay, explain the role of action potentials in skeletal muscle contraction. Again, I feel like we've kind of already gone over that. So there is a action potential that happens in the motor neuron, right? And then there's an action potential that happens in the skeletal muscle. And it's that action potential that's going to trigger calcium release in the way I outlined here. And just kind of keeping in mind all the different action potentials in your head, you can think of the skeletal muscle action potential as being the exact same as the neuron one. It has voltage-gated sodium and voltage-gated potassium, and all of the things that we talked about with the neuron action potential happens in the skeletal muscle one as well. Okay, number 17, compare and contrast skeletal muscle and cardiac muscle. How do the cellular mechanisms for contraction compare? And how do their action potentials compare? And what is the reason for this difference? So the differences in their cellular mechanisms for contraction are kind of what we were talking about earlier, but I'll just draw it here. So I'll say this is my cardiac muscle cell. This is my skeletal muscle cell. They both have a SR store of calcium. And they both have RYR and a pump. In skeletal muscle, the membrane has a voltage sensor. And in cardiac muscle, it's a calcium channel. And so in skeletal muscle, a motor neuron fires, and then the skeletal muscle fires its own action potential. That activates the voltage sensor. The voltage sensor mechanically opens the RYR, which causes calcium release. And in the cardiac, there is no input from a motor neuron. So cardiac muscle cells will fire an action potential first because of the SA node, right? So if I draw, here's my heart, here's an SA node. So the SA node has a bunch of cells that are firing action potentials at the beat of your heart, right? Your pacemaker cells. So they're kind of dictating when the action potentials happen. And then that voltage that voltage change is sensed by the cardiac muscle cells nearby, and that causes a cardiac muscle action potential in those cells nearby. And then because all of the cardiac muscle cells are connected by gap junctions, all of those changes get translated to the next muscle cell, and that one fires an action potential. The next one. So they're not directly innervated by neurons. They have like one starting point that is generating action potentials, and then that gets communicated to the cells nearby, and then you just have this kind of ripple effect because all of the cells are connected via those gap junction tubes. But so you have in the cardiac cell also an action potential, but it looks kind of weird. It has like a big plateau. But that action potential comes in, and that's going to trigger the calcium channels to let in a little bit of calcium. And in this case, the RYR receptor is opened by calcium. It's a calcium gated calcium channel. So that calcium coming in triggers calcium release from the RYR. So that shows you kind of the difference between the two types of cells and how they get calcium into the cytoplasm. And then what calcium does in the cytoplasm by binding to actin to allow myosin to bind and to cause the power stroke, that's all the same in both of them. So the difference is just kind of that voltage sensor versus the calcium channel, and then also the shape of the action potential. So the shape differs because this shape allows a muscle to contract and very quickly reach tetany, whereas this action potential actually prevents tetany from happening, so that you get just little pulses of contractions instead of a heart that is like contracting with a sustained force, which is just not what we want for the heart. Yeah, question?
Oh, in terms of the funny current, do both skeletal and cardiac muscle have funny current then? Or I thought only cardiac muscle had funny current.
Yeah, so actually both of these cells do not have funny current. So the only one that has funny current is the SA node cells. So if I were to like draw a heart, there's the SA node. And if you were to zoom in on that SA node, you have cells that are firing continuously. And the reason why they're firing that way is because of the funny current. And then all of the rest of the cells of the heart, they do not have the funny current. They're firing like this one. Does that make sense?
Okay, so the relevance of the funny current is that it just helps keep the heart rate going, like the SA node is like in line with the heart rate. Is that what the leaky channel does then?
Yeah, the
sodium
SA
leaky channel.
node
Okay.
sets the heartbeat. So whatever the frequency of the SA node's action potentials, that's the frequency of the heartbeat. Okay, yeah, so action potentials compare, they look very different. And the reason is for skeletal muscle, we actually want to reach tetany to where we can like, hold that contraction. And if you have action potentials that are really short, then you could have a bunch of them come in really quickly after one after another. And that's going to cause that sustained temporal summation tetany response. Whereas if you have action potentials that are so long that you actually can't ever make them fire super fast, then you prevent a sustained contraction like you get in tetany. And that's ideal because you don't ever want your heart to just sustain a contraction, because the whole point is that it's pumping blood, not just contracting. So the way the action potential looks matches the function of those muscle cells. Yeah, question?
So I'm just clarifying, when we're talking about the cardiac system, is that action potential what's allowing that calcium channel to initially open and let the calcium in to set everything else into motion? Or is that calcium channel like a pore that's always open and it just happens to be like put in and the mechanism's different?
So this action potential coming in triggers that calcium channel.
Okay. All right. So it's not going to always be open. It'll just be when that action potential comes.
Yeah.
Thank you.
You're welcome.
Thanks.
Okay. What are the basic steps in a heartbeat? From SA node signal to blood leaving the heart. So yeah, step one is SA node fires. And that's the one that's firing these continuous action potentials. And the reason why they're continuous and you don't ever have like a resting state is because you have these sodium channels that are activated by hyperpolarization. So as the membrane potential goes down, those sodium channels open back up and cause the membrane potential to move up. And so if this is my heart, after the SA node cell fires, and that's going to cause all of the cells nearby it to fire action potentials. And like I said, that firing is just going to spread to the other cells because they're all connected to each other. So you start at the SA node, and it just kind of ripple effect causes all of the cells of the heart to contract. And there's also this little side path where cells in the SA node get connected down to cells towards the bottom of the heart. So it causes, when the SA node fires, the ventricles actually fire from the bottom, moving upward. Yeah, question?
So when the action potential in when the SA node produces an action potential, the action potential propagates out to all of the cells in the atria, and then also goes down into the Purkinje fibers or whatever they're called, and that's why it contracts from the bottom up.
Yes, exactly.
Okay.
Yeah.
Thank you.
And so as soon as you get the propagation to outside the SA node, you should know that now the action potential has that weird look. So all of the other muscle cells, whether it's in the atrium or the ventricle, they do that weird plateau action potential. And they're not firing continuously necessarily. They're not setting the beat. They just fire at the rate that whatever the SA node says. Okay, and so then after that, you need to kind of know the basic kind of bulk flow that happens in the heart in response to these contractions. So here is going to be my beautiful drawing of the heart. Okay, so this is my right atrium, right ventricle, left atrium, left ventricle. And so how is blood going to travel? So we're going to have deoxygenated blood enter into the right atrium. And then, oops, sorry, my drawing is a little bit wrong. There we go. Okay, so blood's going to come in from the body, deoxygenated, into the right atrium. And then we're going to have contractions of the atriums and then the ventricles, right? So atriums contract first and then the ventricles. So the right atrium is going to contract. And when that happens, we're going to have high pressure in the right atrium and lower pressure in the right ventricle. And so it's that high to low pressure that's going to push blood from the right atrium to the right ventricle. So again, it's pressure that is determining bulk flow. But it kind of just makes sense, right? If you imagine kind of squeezing the right atrium, it makes sense that blood's going to flow down into the ventricle. And so also when you squeeze or contract the right atrium, that's going to open up these valves. So in order to open these AV valves, you have to have this high to low pressure. So the valves that are in between, oops, I'll do a different color. The valves that are in between the atrium and the ventricles, those are our AV valves. Ooh, that's an ugly color, oh well. And then the valves between the ventricles and out of the heart, those are the semilunar valves. Okay, so blood moves high to low after the atrium contracts. And then you can imagine we have all this blood in the right ventricle, and now the right ventricle is going to contract. When the right ventricle contracts, now what have we done to the pressure? We've made the pressure really high here and relatively low here and here. So if we have really high pressure in the right ventricle because we're contracting it, and lower pressure in the atrium, that will actually shut the valves closed. And if we have high pressure here and lower pressure here, that's going to open that valve and cause blood to move through the semilunar valves out into the pulmonary artery. So it's all high to low pressure. Initially high pressure in the atrium because that's contracting, and then high pressure in the ventricle because that contracts next. And that's going to push the blood all in the right direction, from outside the body to the atrium, to the ventricle, and then out to the pulmonary artery. And the little side important point is, you can imagine if we contracted the ventricle, it could move blood, out to the pulmonary artery or back into the atrium. And it's actually kind of the way that these valves are shaped, kind of move in that V, that if you put a high amount of pressure in the ventricle, it causes those valves to shut. And if they didn't shut correctly, then you could get blood moving in the wrong direction. So one thing I could see him asking you about is, what would happen if I change the pressures in one of these areas, or what if I messed with the valve? So if you mess with the valve, like if the valve doesn't work, then what I would say is less blood is going to move out into the pulmonary artery like I want it to, because some blood is going to move back into the atrium because the valves aren't closed correctly. So we're going to end up having less blood leaving the heart than we want to. As far as if he asked about like changing pressure, let's say, I don't know why it changed to highlight. Let's say we change the pressure of the right ventricle to where instead of having a slight delay in when it contracts at the exact same time as the atrium. Well, that would mess up the high to low pressure that would cause the movement of the blood. If you made it high and high in both the atrium and the ventricle, then there's less of a bulk flow driving force to move from the atrium to the ventricle. So again, I would say that changing the pressure in that way would cause less blood flow from the atrium to the ventricle. So be prepared for questions like that, where I change the pressure in one of the chambers, and you should be able to tell me how that will affect blood flow. And similarly, if I mess with the valves, what will that do? And so I just want to also mention that I've been focusing on the right ventricle and the right atrium, but in reality, both sides are contracting and relaxing at the same time. So at the same time we were doing, contraction of the right atrium, we're also contracting the left atrium, which means blood is going to flow in here, again, from high pressure to low pressure. And then after the left atrium contracts, the left ventricle will contract with some delay. Once the left ventricle contracts, then we have really high pressure here and lower pressure in the aorta, lower pressure in the right atrium, lower pressure in the atrium. The lower pressure in the atrium compared to the ventricle will cause these shutters to close. And the high pressure here and the low pressure here will cause these shutters to open and blood will be able to leave. So again, the focus should be on, that it goes atrium, ventricle for contract, contract. And blood is going to go from the outside of the body to the atriums, then to the ventricles, then back out through the pulmonary artery or the aorta, according to pressure differences. And the reason why pressure changes is those contractions. So if you contract an area, if you contract a chamber, you're making that area high pressure. And you need high to low pressure in order to get the blood to move. Okay.
Oh, I have a question.
Yeah.
As far as terminology goes, are we pretty much going to be given all the terminology we need? Is it more like just conceptually how the pressures work and everything?
Yes. Yeah. I would say, yeah, you won't have to memorize any of the parts, but you should know, like if I change the pressure of the pulmonary artery, make it higher or lower, can you tell me how that's going to change blood flow?
Okay. And then earlier, I remember you were saying like whenever muscles contract, they're at tetany. Is that what you said? Like,
yes.
Any contraction is tetany?
For a skeletal muscle, yeah.
Okay. Okay, thank you.
You're welcome. Okay. Move on to the next thing. Ugh. Oh, look, we're at the end. So exciting. Okay. Let me erase. I think that's good enough. Okay, so this is just asking you to like think about the different action potentials we've talked about in class. So think about when they are relevant and how and why they differ. So the neuron action potential. So that is the one that looks like that classic action potential, and it's really dictated by voltage gated sodium channels and voltage gated potassium channels. And it's relevant because, at least with what we've been talking about, motor neurons fire action potentials that then get communicated to skeletal muscles. So then we have skeletal muscles that fire their own action potential in response to the motor neuron action potential. And this is supposed to look exactly like the other one. It's also voltage gated sodium and voltage gated potassium. Okay, and then we can switch over to thinking about the heart. And so we have the SA node. Oops. The SA node cells, and they have super weird action potentials that look like this. And the reason for that is they have a weird, funny current. Let me see if I can pull something up. Share screen. This is from your book, but it shows you the pacemaker action potential, and you can see that this is also a little bit different in that the action potential itself is mostly due to calcium and not so much sodium. I just wanted to show that to you guys. So the funny current is sodium channels that kind of cause this slow rise, but there's also a little bit of calcium causing that slow rise, and then the actual quick increase is due to calcium channels as well. And then the decrease is voltage gated potassium. So SA node cells thing that you should know about is they have this funny current that makes the membrane potential constantly go back to depolarizing and never actually rest down. And then the last one is the cardiac action potential. That looks like this. And again, I'm going to go ahead and show you that one as well. Oops. So this one you can see is a little different in that it's the depolarization phase is also triggered by the voltage gated sodium channels, like for neurons and skeletal muscle. But then you have this weird calcium current right here, where you get these calcium channels that open and they don't close very quickly. And that causes this plateau period in the action potential. And also during this plateau, it's not just calcium current, but there's also some potassium current and even a little bit of sodium as well, which is why the membrane potential isn't just moving up towards calcium's equilibrium potential, but because it's still doing a kind of tug of war battle with these other ions that are also conducting. And then eventually the calcium channels turn off, they close, and we get more voltage gated potassium coming online, and that causes this decrease in the membrane potential. So oops. All that to say, this is slightly different in we have this is being caused by sodium. This is being caused by calcium and potassium. And this is being caused by voltage gated potassium. And the fact that you're getting a minus of calcium, right? The calcium channels go offline. So those are all the action potentials that we talked about. Yeah. And I'll just move on to, well, do y'all have any questions about the action potentials? All right. Okay, last thing to know about is the map equation. So specifically what you should know about the map equation is it's a way to calculate the mean arterial pressure in your arteries. And the reason why we calculate it is because changes to the mean pressure will cause some kind of regulatory response by the body. So there are three kind of examples to how we might see changes to the pressure that you might see come up on the exam. So I'm just going to go over those three. There are many ways you can change the pressure, but I'm going to whittle it down to three possible ones you could see. So one could be you get low blood pressure. So if you have low blood pressure, that's going to trigger a sympathetic nervous system response. Ah. And the sympathetic nervous system is going to do two big things. So what it's going to do is cause vasoconstriction. Yeah. And it's also going to increase SA node action potential frequency. So how do these relate to the MAP equation? So if you increase the action potential frequency of the SA node, what you're doing is changing heart rate. That's going to cause heart rate to go up, which if you look at the MAP equation will mean the mean arterial pressure will go up. So in response to pressure going down, this is a response that causes heart rate to go up and therefore mean arterial pressure to go up. Yeah, question?
So should we know like the definitions and the equation of the MAP equals SV times HR TPR, or should we just know basically what you're demonstrating, that if you have low blood pressure, then there's a response where you get vasoconstriction and increase in SA node AP frequency?
Yeah, you should understand it just conceptually, not necessarily like memorizing the equation or plugging in numbers with the equation.
Okay, thank you.
Yeah, so you just need to know like, oh, increase in heart rate, that is going to affect the pressure by causing it to go up. That's the only reason why the equation's useful. And then same with like vasoconstriction. You should know that what vasoconstriction is going to do is it's going to increase TPR. So TPR is just total peripheral resistance, and it's just how much resistance exists in your blood vessels. And if you constrict them, you have a higher resistance. So this going up is going to cause mean arterial pressure to also go up. So the sympathetic nervous system causes a response to cause mean arterial pressure to go up in the case of low blood pressure. Okay, 2 would just be high blood pressure. And it's just kind of the opposite. So high blood pressure is going to trigger your parasympathetic, I'm not going to write it all out because my pen doesn't really work, parasympathetic nervous system, and it causes a decrease in SA node action potential frequency. So now you get it firing like this instead of super fast. And that's going to cause the heart rate to go down, which causes mean arterial pressure to go down. And it also causes vasodilation, which causes resistance to go down in your blood vessels, which means TPR goes down. Okay, so you should be able to relate, like, if I tell you one of these changes, can you tell me, like, what is the response going to be in the body and how will that change heart rate and total peripheral resistance? Now, you should also be prepared for an example that changes stroke volume and how that would change mean arterial pressure. And so the example that I want you to know is by changing aortic pressure. So stroke volume is, if I withdraw my little badly drawn heart thing here. So the left ventricle sends blood out through the aorta. So this tube here is the aorta. And stroke volume refers to how much blood gets pumped out of the left ventricle per beat. So if you have a ton of blood being pumped out of the left ventricle to the aorta, then you have a higher pressure, right? If you go to the equation, you increase stroke volume, you increase mean arterial pressure. If you decrease stroke volume, so less blood is coming from the left ventricle, then you actually decrease pressure. So one way you could see this come up, or one way I've seen it come up in the past, is if you change the aortic pressure. So let's say we make the aortic pressure, let's just do both. Let's say it's low. Some change has happened, I don't know, that causes the pressure in the aorta to be lower. Well, what you should think is, okay, using my flux reasoning, if it's high pressure here and low pressure here, but it's now super low here, I would expect there to be more flux from the left ventricle to the aorta, right? So more blood leaving if we make this low value even lower. If more blood is leaving, then I'm increasing my stroke volume, which will increase mean arterial pressure. Similarly, if I say for some reason the aortic pressure is high, then we need it to be high here and low here. So if we make this too high, then I've decreased the driving force to move from the left ventricle to the aorta. And I'm going to say that the total volume of blood leaving the left ventricle is going to be less because the bulk flow is less. So the stroke volume will go down, which means the mean arterial pressure will go down. Yeah, and so I think that also gets at the point of like, if I say I change pressure in the pulmonary artery or the aorta or the atrium, you need to know the pathway in the heart of like where blood is traveling from high to low in each point in order to answer those questions. So it's not that you need to, we're not going to test you like, where's the aorta? But in order to tell me what is the consequence of aorta pressure going up or down, you need to know where the aorta is and where it's getting blood from and where it's sending blood to, if that makes sense. So like heart anatomy will come up in that way on the test. Yeah, question?
Oh, this is a different question. I was wondering if we can go over question 15 again. I was really confused on that.
Yeah. Oh. So it's hard to see, but it says if skeletal muscle only operates at tetany, which of the graphs from this week's lab would never be produced in a live animal? And it would be graph 2. So where you saw a bunch of little bumps leading up to some maximum displacement, you would never get in an animal muscles being recruited in that way where the motor neuron that was communicating with them was changing frequency.
But so like if it's like building upon each other, right? Would it like eventually reach tetany though?
Yeah, so it just immediately is at tetany because we're never stimulating it at a different frequency. We're always, if a motor neuron is talking to a muscle, it's talking at this really fast rate. It's never gonna like slightly fire and then fire more. It's always like firing a ton. So it's always
So would it be,
max
I
value.
see. So would it just be like a horizontal line, like it would never go down?
Yeah, it would be a non-bumpy line because it couldn't like I mean it goes from, you know, having a relaxed muscle, no calcium, to having calcium. But it wouldn't ever be like a bumpy line.
I
It would
see.
be like a smooth increase in calcium only. Yeah, another question?
When you're talking about the map equation, if your heart rate is increasing but your TPR is decreasing, how do you know that map is overall increasing?
You said if what's increasing and what's decreasing?
Like if it's sympathetic and you said that, sorry, if it's sympathetic and you said that the heart rate is increasing and TPR is increasing, why does like restriction, like if it's getting more restricted and there's more resistance, why does that increase map?
Just because if you have smaller tubes and the same amount of blood, that's going to be more blood pressing up on the vessels if you have really narrow tubes. So that causes more pressure. Whereas you can imagine if you had like these giant tubes and the same amount of blood, you probably wouldn't have that much pressure on the tubes if they were really big.
Thank you.
You're welcome.
Thank you.
Yeah. If y'all have other questions that you want me to address, let me know, or if you want to go over anything else.
I was gonna ask, for for question number 150 on Piazza, you did like a example, I think, and I was wondering if you could like go over that. I can't find it right now, but it's number 150.
Let's see. How do I see the numbers? Oh, I found it. So do you want to go over like the little example I gave?
Yeah. Would you be able to say like what the title is? Because I cannot.
Electrical gradient.
Okay.
Yeah, it's electrical gradient posted at.
I found it.
Okay, yeah.
Yeah. We were oh gosh, what were we saying? Sorry, I did this with friends, so we're trying to like remember. Because we thought it's a negative. We thought that the total membrane potential, like it would be -80 when you do the like Ernst equation. And then so you would do like +20 minus -80. So then the membrane potential would then be 100. And because the charge is -1, that would drive the action, like that would drive it into the cell, right?
Wait, so it was. What did you get for the equilibrium potential?
-80.
-80.
Okay. So then it's 20 minus -80. So the overall driving force is +100. Did you get that?
Yes.
Yeah, and then because it's a negative charge, it's inward.
Yeah, okay, cool. I think glad to have that confirmed because like all of the like test your like knowledge ones, it's hard because there's not always an answer, but thank you. Okay, I think that was.
Of course, yeah.
Oh, actually, I do have another question.
Yeah.
So we have, so in lecture, he went over like ataxia and kind of like how it was a difference in like when the potassium pumps like opened, or like were fully open, I think, or something like that. Are we gonna need to know anything about like that particular case, or more just like what happens if the potassium pump opens at a higher voltage?
So potassium channel.
Yeah.
Yeah, you wouldn't have to know that specific example. In fact, I'm sure he won't give any examples you've seen before.
Okay, cool.
All right. Yeah, I'll stick around if anyone has any more questions, but otherwise, that is all. And I will try to upload this quickly after. And
Thank you.
also post on Piazza. I'll be watching Piazza as well.
Thank
Oh,
you.
excuse me.
Yeah.
Thank you.
Of course.
Hi, do you know if you can post the note sheet you were using or share that as well?
Yeah. Where would Piazza work?
Yeah, that'd be great. Is that where you post the video too, the recording?
Well, I usually do it as an announcement, but apparently y'all can't get it sometimes as an announcement.
I saw it in the notification.
I'll post it as an announcement and then also as a Canvas message and then also as a Piazza.
Okay.
He has
Thank you.
disabled announcements for some reason, so you can't really see those. That's why I think those guys were talking about that.
Yeah, how did y'all get here? Because I posted this.
Oh, if I got an email, I have it set up so that I get emails for every notification. So I saw the announcement as an email. I just clicked the link.
Oh, okay.
But if you can't see
Yeah,
it,
I got the notification, but I don't know.
Okay.
Yeah.
Yeah, question?
So you know how you said that animal or the skeletal muscles only operate in tetany?
Yeah.
So you wouldn't see like that, like it would go up and up and up and up. It would just like go up all at once.
Yeah.
I thought like temporal summation was that it goes up and up and up like that. Or is like temporal like I thought that's how it like happens, or no?
It's just that in real life, when motor neurons are firing, they fire at such a high rate. It's like you skip the bumpy part and you just go straight to that top part. So it's just that.
Oh, so it is still like.
It could happen, but it's.
Oh, so it is like consecutive still. It's just like so fast that you don't see it.
Yes, yeah, exactly.
Oh, okay. Thank you.
You're welcome.
Hey, real quick.
Yeah.
Just from like your overall like questions that you just gave to all of us, what would you say is the heaviest topic? And what like would you say to like extra focus on, if you can say?
I mean, I designed it after I got to look at the test, so I really tried to hit everything that's on the test. I guess you really need to know the ion movement. I would say that's the heaviest part, but I would say kind of it's equally spread throughout the topics I posted.
Okay, awesome. Well, thank you for your help. It was great. I appreciate your time.
I'm glad it helps. Question.
Yes, one more quick question. So we were looking at the end of lecture 8 on the membrane transport the last page. It's like page 23 in the lectures. And it's asking about the symporter for sodium and iodine. And then there was a test your understanding question about like if the driving force of iodine is greater than the driving force of sodium, would a symporter be able to like switch directions in that sense? Because we know it's using the driving force of one to bring the other against its gradient. But
Yeah.
if the driving force is switched, would that switch the directions?
Yes, it would switch the directions. So the symporter has like two ions, one that's moving against its gradient, one that's moving passively. So the passively moving one, it's only moving based on whatever the concentrations are. So if you, flip the concentrations for that ion, and it moves in the other direction, then it will.
Okay, thank you.
You're welcome. Yeah, other question?
Hey, I was wondering if you could go over all the like different parts of the heart anatomy and like do we need to know about like the atrial and the atrial like arteries, atrial capillaries, and the venules and all of that stuff? Do we need to know that, or just the part of the heart exactly?
Only what I went over. So like you need to know the SA node has the pacemaker cells. You need to know the atriums and the ventricles. You should know the right ventricle sends to the pulmonary artery, goes to the lungs, and the left ventricle goes to the aorta, to the rest of the body. And you need to know blood is going to move from outside of the body to the atriums, then to the ventricles, then back out either to the pulmonary or to the aorta. So you should know that pathway. And you should know that as it's moving through that pathway, the reason blood is going from one section to another is because it's moving from high to low pressure. So that's what's going to come up on the test.
Okay, could you explain the SV again, like the stroke volume part where it talks just a specific bit. So for example, if it's going to the pulmonary vein, or let's say talk about the aorta again. So if it's going to the aorta and you have high pressure in the aorta, then like it's higher pressure, that means less of it is going to move, and that changes the stroke volume. So if I were to move down a level, like for example, if I were to go from an atria to a ventricle and I have higher pressure, it doesn't move back, right? So that wouldn't affect the stroke volume then because of the valves.
So tell me what your example is.
So the stroke, I was just wondering, stroke volume can only be changed when you're going from the ventricle to the aorta, right? Because going from ventricle to atrium is not possible because of the valves. And I was also wondering how that would work because, or is like, I'm not really sure. Like, wouldn't the valves stop anything from like going backwards? So you wouldn't really have a backward pressure. That's what I was trying to understand.
Yeah, so I mean, it depends. What you should keep in mind is the valves only close if the pressures are correct, right? So what causes this to close is if there's a lower pressure here and a higher pressure here. That high pressure in the ventricle compared to the atrium, that has to be there in order for these to close. So if you change that to where maybe this stays high So if you have a really high pressure here, then these are not going to close properly. So yeah, you could get the, you know, you could be given a situation on the test where the atrium, maybe it stays contracted. And it's just, for some reason, I don't know, it sustains a contraction. That would cause high pressure here that stays high, that could cause these to stay open. And then when the ventricle contracts, it's not only going to send blood here, but also back this way, possibly.
Wait, but if that's high and when you contract, your pressure gets higher, why would it send it back?
Yeah, it would depend on the relative pressure. So if it was,
Okay, well,
so I think if you imagine the ventricle, which is much bigger than the atrium, if the atrium is contracted and the ventricle contracts, yeah, I would say the pressure in the ventricle is always going to beat out the atrium. So it probably would end up closing it and probably wouldn't matter. I can't imagine you getting the pressure so high in the atrium that it would keep it open.
so just to repeat the question again. So then when we're talking about SV, we're only worrying about ventricle and aorta and the ventricle and the pulmonary vein then?
Yeah.
Okay. Makes sense. Thank you so much.
You're welcome.
This was really helpful.
Oh, I'm so glad. Thank you for saying that.
Yeah.
All right, any other questions?
I was just gonna ask if you're gonna be posting the recording of this.
Yes, for sure.
Okay, cool. I just missed like most of it, so I just wanted to make sure. I thought like the recording would be already posted, so I came back to check if it's still going on, and I was like, wow.
Yeah, yeah. No, yeah, I should probably end it right now. That way I can upload this.
All right, thank you.
You're welcome. Any last minute questions?
Thank you.
Cool.
All right.